Solving Simultaneous Equations, Linear and Quadratic. A comprehensive guide to solving systems with one linear and one quadratic equation. Lesson Overview. Core Concepts. Understanding the substitution method for linear quadratic systems. Worked examples. Step-by-step solutions to various problem types. Word problems. Real-world applications and problem-solving techniques. Practice problems. Exercises to reinforce understanding. Key insight: the substitution method. For systems involving one linear and one quadratic equation, the substitution method is the fundamental analytical approach to finding solutions. The substitution method. Step 1. Make a variable the subject in the linear equation. Step 2. Substitute this expression into the quadratic equation. Step 3. Solve the resulting quadratic equation. Step 4. Substitute the values back to find the corresponding values of the other variable. Example 1. Basic substitution. Given equations: 3x plus y equals 10, 2x squared plus y squared equals 19. Step 1. Make y the subject in the linear equation. From the first equation, 3x plus y equals 10. Subtracting 3x from both sides gives y equals 10 minus 3x. This is obtained by isolating y in the linear equation. Step 2. Substitute into the quadratic equation. Take the expression for y, which is 10 minus 3x, and replace y in the second equation. So, 2x squared plus y squared equals 19 becomes 2x squared plus open bracket 10 minus 3x close bracket squared equals 19. This is derived by direct substitution of y into the quadratic equation. Now expand the bracket. Open bracket 10 minus 3x close bracket squared equals 100 minus 60x plus 9x squared. This results from squaring the binomial using the expansion formula, so the equation becomes 2x squared plus 100 minus 60x plus 9x squared equals 19. This follows from replacing the squared bracket with its expanded form. Now collect like terms. 2x squared plus 9x squared equals 11x squared. So the full equation is 11x squared minus 60x plus 81 equals 0. This is simplified by combining the x squared terms and bringing all terms to one side of the equation. At this point, we have reduced the system of equations into a single quadratic equation. 11x squared minus 60x plus 81 equals 0. Example 1. Solving the quadratic. Start with the quadratic obtained earlier. 11x squared minus 60x plus 81 equals 0. This is stated as the quadratic we will factor and solve. Factor the quadratic by grouping. 11x squared minus 33x minus 27x plus 81 equals 0. This is obtained by splitting the middle term negative 60x into two terms, whose coefficients multiply with 11, to give the product of the first and last coefficients. 11x open bracket x minus 3 close bracket minus 27 open bracket x minus 3 close bracket equals 0. This is derived by factoring out 11x from the first two terms and factoring out negative 27 from the last two terms. Open bracket 11x minus 27 close bracket open bracket x minus 3 close bracket equals 0. This is simplified by factoring out the common binomial factor x minus 3. Find the x values from the factored form. 11x minus 27 equals 0, or x minus 3 equals 0. This results from the zero product property, which states that if a product of two factors equals 0, then at least one of the factors must be 0. Solving 11x minus 27 equals 0 gives x equals 27 over 11. This follows from adding 27 to both sides and then dividing both sides by 11. Solving x minus 3 equals 0 gives x equals 3. This is obtained by adding 3 to both sides to isolate x. Substitute each x back to find y. When x equals 3, y equals 10 minus 3 times 3, which equals 10 minus 9, which equals 1. This is derived by substituting x equals 3 into the linear relation y equals 10 minus 3, x, and simplifying. When x equals 27 over 11, y equals 10 minus 3 times 27 over 11, which equals 10 minus 81 over 11, which equals 110 over 11, minus 81 over 11, which equals 29 over 11. This is simplified by writing 10 as 110 over 11, subtracting 81 over 11, and combining the fractions. Solutions. The solution pair 1 is, open bracket 3, 1, close bracket. This is the integer solution found by substitution. The solution pair 2 is open bracket 27 over 11, 29 over 11, close bracket. This results from the exact fractional values obtained for x and y. Example 2. Product relationship. Given equations. 3x plus 4, y equals 11. X multiplied by y equals 2. Step 1. Make y the subject in the first equation. From 3x plus 4y equals 11, subtract 3x from both sides to get 4y equals 11 minus 3x. This is obtained by rearranging the linear equation to isolate terms in y. Now divide through by 4 to make y the subject. So y equals open bracket 11 minus 3x close bracket over 4. This is simplified by dividing each term by 4. Step 2. Substitute into the second equation. Replace y in the equation x multiplied by y equals 2 with the expression open bracket 11 minus 3x close bracket over 4. This gives x multiplied by open bracket 11 minus 3x close bracket over 4 equals 2. This follows from direct substitution of y. Multiply both sides by 4 to remove the denominator. This gives 11x minus 3x squared equals 8. This is obtained by expanding the product and clearing the fraction. Now bring all terms to one side. Negative 3x squared plus 11x minus 8 equals 0. This is simplified into standard quadratic form. At this stage, the system reduces to the quadratic equation. Negative 3x squared plus 11x minus 8 equals 0. Example 2. Finding solutions. Start with the quadratic in standard form. Negative 3x squared plus 11x minus 8 equals 0. This is stated as the quadratic we will factor and solve. Factor the quadratic by splitting the middle term. Negative 3x squared plus 3x plus 8x minus 8 equals 0. This is obtained by writing 11x as the sum of 3x and 8x so that grouping will work. Factor by grouping the first two terms and the last two terms. Negative 3x open bracket x minus 1 close bracket plus 8 open bracket x minus 1 close bracket equals 0. This is derived by factoring negative 3x from the first pair and factoring 8 from the second pair. Factor out the common binomial factor, x minus 1, open bracket x minus 1, close bracket, open bracket negative 3x plus 8, close bracket equals 0. This is simplified by taking the common factor x minus 1 outside the grouped expression. Find the x values from the factored form. X minus 1 equals 0. Or negative 3x plus 8 equals 0. This follows from the zero product property, which states that if a product equals 0, then at least one factor must be 0. Solve x minus 1 equals 0 to get x equals 1. This is obtained by adding 1 to both sides to isolate x. Solve negative 3x plus 8 equals 0 to get x equals 8 over 3. This results from subtracting 8 from both sides to get negative 3x equals negative 8. And then dividing both sides by negative 3. Substitute each x back to find y. When x equals 1, y equals open bracket 11 minus 3 times 1 close bracket over 4, which equals 8 over 4, which equals 2. This is derived by substituting x equals 1 into y equals open bracket 11 minus 3x close bracket over 4 and simplifying the arithmetic. When x equals 8 over 3, y equals open bracket 11 minus 3 times 8 over 3 close bracket over 4, which equals open bracket 11 minus 8 close bracket over 4, which equals 3 over 4. This is simplified by cancelling the 3 in the product 3 times 8 over 3, subtracting, and then putting the result over 4. Solutions. The first solution pair is open bracket 1, 2 close bracket. This is the integer solution obtained from the first factor. The second solution pair is open bracket 8 over 3, 3 over 4 close bracket. This results from the fractional solution obtained from the second factor and its corresponding y value. Alternative approach, using special forms. Given equations, 3x minus y equals 3, 9x squared minus y squared equals 45. Recognize the pattern. Notice that 9x squared can be written as open bracket 3x, close bracket squared. So the second equation becomes open bracket 3x close bracket squared minus y squared equals 45. This is obtained by rewriting 9x squared in terms of 3x squared. This is a difference of 2 squares. This follows from the standard identity a squared minus b squared equals open bracket a minus b close bracket, open bracket a plus b close bracket. Factor the difference of squares, open bracket 3x minus y close bracket, multiplied by open bracket 3x plus y close bracket, equals 45. This is derived by applying the difference of squares factorization. Substitute the first equation. From the first equation we know 3x minus y equals 3. So substitute this into the factorized form. This gives 3 multiplied by open bracket 3x plus y close bracket equals 45. This is simplified because 3x minus y is replaced by 3. Now divide both sides by 3. This gives 3x plus y equals 15. This is obtained by cancelling the common factor of 3 on both sides. Solve the new system of equations. We now have 2 simultaneous linear equations. 3x minus y equals 3. 3x plus y equals 15. These form a system that can be solved easily, since the y terms can be eliminated by addition. Alternative approach, solution. Add the 2 equations together. 3x minus y equals 3. 3x plus y equals 15. Adding these gives 6x equals 18. This is obtained because negative y and positive y cancel out, leaving 6x on the left-hand side, and 3 plus 15 equals 18 on the right-hand side. Solve for x. 6x equals 18. Divide both sides by 6 to get x equals 3. This follows from isolating x by dividing through by the coefficient 6. Substitute back to find y. Take the equation 3x plus y equals 15. Substitute x equals 3 to get 3 times 3 plus y equals 15. This simplifies to 9 plus y equals 15. Subtracting 9 from both sides gives y equals 6. This is derived by isolating y after substitution. Final solution. X equals 3 and y equals 6. This is the single solution that satisfies both equations. Therefore, the point open bracket 3, 6 close bracket is the only solution to this system. Word problems. Translating to equations. Identify the unknowns. Assign variables to the quantities you need to find. Express relationships. Translate the given conditions into equations. Form a system. Ensure you have as many equations as unknowns. Solve and verify. Apply the substitution method and check your answer. Word problem example 1. Problem statement. The product of 2 numbers is 12. The sum of the larger number and twice the smaller number is 11. Find the 2 numbers. Step 1. Identify the unknowns. Let x represent the larger number. Let y represent the smaller number. This sets up the variables so we can translate the problem into algebra. Step 2. Express the relationships. From the problem, the product of the numbers is 12. So x multiplied by y equals 12. This is obtained from the statement, the product of 2 numbers is 12. Also, the sum of the larger number and twice the smaller number is 11. So x plus 2y equals 11. This is derived from the statement, the larger number plus twice the smaller equals 11. Step 3. Solve the system. From the second equation, x plus 2y equals 11, we can make x the subject, so x equals 11 minus 2y. This follows from subtracting 2y from both sides. Now substitute this value of x into the first equation, x multiplied by y equals 12. This gives open bracket 11 minus 2y close bracket multiplied by y equals 12. This is obtained by replacing x with its expression in terms of y. Expanding gives 11y minus 2y squared equals 12. This results from multiplying y by each term inside the bracket. Now rearrange into standard quadratic form. 2y squared minus 11y plus 12 equals 0. This is simplified by bringing all terms to one side and writing with a positive leading coefficient. At this stage, the problem reduces to solving the quadratic equation. 2y squared minus 11y plus 12 equals 0. Word problem example 1. Solution. Start with the quadratic in standard form. 2y squared minus 11y plus 12 equals 0. This is the quadratic equation obtained from the word problem. Factoring the quadratic split the middle term negative 11y into negative 8y and negative 3y, so the equation becomes 2y squared minus 8y minus 3y plus 12 equals 0. This is obtained because negative 8y minus 3y equals negative 11y. Now factor in pairs. From the first two terms, take out 2y to get 2y multiplied by open bracket y minus 4 close bracket. From the last two terms, take out negative 3 to get negative 3 multiplied by open bracket y minus 4 close bracket. This is derived by grouping terms to make a common factor visible. Now factor out the common binomial factor, open bracket, y minus 4 close bracket. This gives open bracket 2y minus 3 close bracket, multiplied by open bracket, y minus 4, close bracket equals 0. This is simplified by removing the shared factor, finding the y values, set each factor equal to 0. 2y minus 3 equals 0, or y minus 4 equals 0. This follows from the zero product property. From 2y minus 3 equals 0, we get y equals 3 over 2. This is obtained by adding 3 to both sides and dividing by 2. From y minus 4 equals 0, we get y equals 4. This is derived by adding 4 to both sides. Finding the x values. When y equals 3 over 2, substitute into x equals 11 minus 2y. So x equals 11 minus 2, multiplied by 3 over 2 which equals 11 minus 3 which equals 8. This is simplified by cancelling the 2 and then subtracting. When y equals 4, substitute into x equals 11 minus 2y. So x equals 11 minus 2 multiplied by 4, which equals 11 minus 8, which equals 3. This follows from multiplying and subtracting. Solutions. The first solution pair is open bracket 8, 3, over 2 close bracket. The second solution pair is open bracket 3, 4 close bracket. Both satisfy the given conditions from the word problem. Since x represents the larger number in the problem statement, both solutions are valid. This is because in the first solution, 8 is larger than 3 over 2, and in the second solution, 4 is larger than 3. Word problem example 2. Problem statement. Find a two-digit number, such that 2 times the tens digit is 3 less than thrice the unit digit, and 4 times the number is 99 greater than the number obtained by reversing the digits. This restates the problem in full words, so we can form algebraic relations. Step 1. Identify the unknowns. Let A denote the tens digit. This assigns a symbol to the tens place, so we can work algebraically. Let B denote the units digit. This is obtained by assigning a symbol to the units place for the same reason. The original two-digit number is 10a plus b. This follows from positional notation. The tens digit contributes 10 times its value, and the units digit contributes its own value. The reversed two-digit number is 10b plus a. This results from swapping the digits so the original units digit becomes the tens place and vice versa. Step 2. Express the relationships. First condition. 2 times a plus 3 equals 3 times b. This is obtained directly from the sentence. 2 times the tens digit is 3 less than thrice the unit digit. Rewritten, so that the equality is explicit. Rearranged to standard linear form, 2a minus 3b equals negative 3. This is derived by bringing the term 3 times b to the left-hand side, and subtracting 3 from both sides to isolate terms. Second condition. 4 multiplied by the number 10a plus b, minus the reversed number 10b plus a, equals 99. This is obtained from the phrase 4 times the number is 99 greater than the number obtained by reversing the digits, rewritten as an equation. Simplify the left-hand side to obtain 39a minus 6b equals 99. This is simplified by expanding 4 times 10a plus b to give 40a plus 4b, subtracting 10b plus a to yield 39a minus 6b, and keeping 99 on the right-hand side. Resulting system of linear equations. 2a minus 3b equals negative 3. This is the linear relation coming from the first condition. 39a minus 6b equals 99. This is the linear relation coming from the second condition after simplification. Word problem example 2. Solution. Start with the simplified second equation. 39a minus 6b equals 99. This repeats the simplified linear relation from the second condition. Divide every term by 3 to simplify. 13a minus 2b equals 33. This is obtained by dividing the left-hand side and the right-hand side by 3 to reduce the coefficients. Write the system to be solved. 2a minus 3b equals negative 3. This is the first equation from the problem restated in standard form. 13a minus 2b equals 33. This is the simplified second equation we will solve together with the first. Multiply the first equation by 2 to eliminate b later. 4a minus 6b equals negative 6. This is derived by scaling the first equation so that the coefficient of b becomes negative 6 and aligns with the other equation. Multiply the second equation by 3 for the same purpose. 39a minus 6b equals 99. This follows from scaling the second equation so its b term also becomes negative 6, enabling elimination by subtraction. Subtract the scaled first equation from the scaled second equation to eliminate b. 35a equals 105. This results from subtracting 4a minus 6b equals negative 6 from 39a minus 6b equals 99, which cancels the b terms and leaves 35a on the left and 105 on the right. Solve for a by dividing both sides by 35. a equals 3. This is obtained by isolating a, dividing 105 by 35 yields 3. Substitute a equals 3 into the first original linear equation to find b. 2 times 3 minus 3b equals negative 3. This is derived by replacing a with 3 in 2a minus 3b equals negative 3. Simplify the left-hand side. 6 minus 3b equals negative 3. This follows from multiplying 2 by 3 to get 6. Isolate the term in b by subtracting 6 from both sides. Negative 3b equals negative 9. This is obtained by moving 6 to the right-hand side, yielding negative 9. Divide both sides by negative 3 to solve for b. b equals 3. This is simplified by dividing negative 9 by negative 3 to isolate b. Final answer. The two-digit number has tens digit a equal to 3 and units digit b equal to 3. This is the result of solving the system for a and b, therefore the two-digit number is 33. This is the single two-digit number that satisfies both given conditions. Geometric interpretation. Linear equation represents a straight line in the coordinate plane. Quadratic equation represents a conic section, circle, ellipse, parabola, or hyperbola. Solutions: the intersection points of these curves. Number of solutions can be 0, 1, or 2, depending on how the curves intersect. Practice problems. Solve the given equations 1 to 5. Additional challenge problem. Problem statement. A woman is Q years old while her son is P years old. The sum of their ages is equal to twice the difference of their ages. The product of their ages is 675. Find the ages of the woman and her son. Step 1. Express the sum-difference relationship. P plus Q equals 2 open bracket Q minus P close bracket. This is obtained by translating the sum of their ages equals twice the difference of their ages into an equation. P plus Q equals 2Q minus 2P. This is derived by expanding the right-hand side 2 times open bracket Q minus P close bracket into 2Q minus 2 pages. 3P minus Q equals 0. This results from bringing like terms together. Adding 2P to both sides and subtracting Q from both sides gives 3P minus Q equals 0. Step 2. Express the product relationship. P multiplied by Q equals 675. This is obtained from the statement. The product of their ages is 675. Step 3. Solve the system. From 3P minus Q equals 0, we get Q equals 3P. This is obtained by adding Q to both sides, and then dividing both sides by 1, which isolates Q as 3 pages. Substitute Q equals 3P into P multiplied by Q equals 675. This gives P multiplied by open bracket 3p close bracket equals 675. This is derived by replacing q with 3p in the product relation. 3p squared equals 675. This results from multiplying p by 3p to obtain 3p squared. Divide both sides by 3 to isolate p squared. P squared equals 225. This is obtained by dividing 675 by 3. Take the positive square root, since ages are positive. P equals 15. This follows because the square root of 225 is 15. And we choose the positive root because age cannot be negative. Now find q using q equals 3 pages q equals 3 times 15, which equals 45. This is simplified by substituting p equals 15 into q equals 3p and multiplying. Final answer. The son is 15 years old, and the woman is 45 years old. These are the positive integer ages that satisfy both the sum difference and product conditions. Key takeaways. Substitution method. Always use substitution for linear quadratic systems. Factoring skills. Factoring quadratics is essential for finding solutions. Special forms. Recognize patterns like difference of squares for efficient solving. Verification. Always check solutions in both original equations. Practice is key to mastering these techniques.